Good afternoon, everyone. Welcome to our new session of Quera with friends. Following our world tour, today we will be presenting about Quera, our partners from Horizon Quantum and Entropica Labs that are based in Singapore. My name is Tommaso Macri. I'm the Executive Account Manager at Quera Computing, and I'm honored to be together with our collaborators, Tommaso De Maria from Entropica Labs. He's the CEO of the company, as well as from Joe Fitzsimmons, CEO of Horizon Quantum. Before starting, let me go through very quickly the agenda of the presentation. I will be starting with a brief overview of the technology and the commercial directions that we are taking at Quera Computing. Then I will give the floor to Tommaso to speak and to present about Entropica, and then the presentation will be followed by Joe that will be talking about Horizon Quantum, and eventually we'll conclude with some remarks on final remarks. Let me start with some very brief information about Quera Computing. Quera is a quantum computing company that is based in Boston, Massachusetts. We are very close to the campus of Harvard and MIT that turned out to be our also very close collaborators. The mission of Quera is to build quantum computers that are based on a specific platform called neutral atoms, which turned out to be also a very promising technology to perform scalable and fault-tolerant quantum computing. And we will be hearing more about the specific direction of the technology more broadly in terms of implementations on several potential platforms from our colleagues. Quera is also collaborating very closely with major cloud providers since November 2022 to deploy and to provide access to our third generation quantum computer. And our computers are nowadays used by a broad number of stakeholders in quantum to address problems from across a number of areas, from quantum simulation to machine learning and combinatorial optimization. Why do we think that neutral atoms are actually relevant for the development of this technology? Well, first of all, neutral atoms are kind of nature's perfect qubits. They are all identical, which means that they respond to external fields all in the same way, so they don't need to be characterized individually like would happen in the case of artificial qubits. They are scalable. Nowadays, we have machines with a few hundreds of qubits. There have been demonstrations actually with 3,000 qubits at Harvard a few weeks ago. And we also believe that the systems can scale to more than 10,000 qubits without requiring complex interconnect technology that is still at the relatively early stage of development. There are also capabilities associated to neutral atoms that allow, for example, for a very efficient encoding of several problems, including in the space of quantum error correction, which is crucial for the reliability of the computation and the execution of very long circuits. Last but not least, our systems operate at room temperature, which essentially means that we do not need to have essentially complex cryogenic devices that might make the access to the systems much more complex from the hardware team, as well as by increasing potentially the footprint of the devices. So none of this is actually necessary, and what we are seeing is the very rapid development, very quick development of the quality and the scalability of our devices. In terms of products, our first generation quantum computer completed about 2 years in November of last year. It's called Aquila. It's still the largest quantum computer available on a public cloud in terms of number of qubits. And over the past 2.5 years, we increased the availability window from about 10 hours at the very beginning of the access to the device in November 2022 to more than 100 hours today. And this essentially allows users from all around the globe to access the system essentially in real time. The use of Aquila has resulted in a number of scientific publications of very high impact. Probably the last one has been published just a few weeks ago on the spring breaking mechanism that is a very relevant process that is inspired by of course, by investigations in high energy physics, and then has now been demonstrated precisely on the device that you see here on the right. The access model that we developed allows also not only academic but also industry users to engage directly with QuEra to develop, starting from proof of concepts to more complex solutions across a number of different areas. And as I was saying at the beginning, we focus mostly on three major areas that can be classified into machine learning or quantum machine learning algorithms, from classification to regression prediction. We developed an algorithm called quantum reservoir computing that exploits at most the capabilities of our quantum hardware. A second area is the one of combinatorial optimization. There are a set of native problems that can be addressed by Aquila that are called maximum independent sets. But there are also other non-native problems, for example, Kubo problems that are relevant for commercial applications that can be mapped into maximum independent sets and thereby solved with the usual tools. The third area, which can be also generalized not only to analog but also to digital quantum computing, is the so-called quantum simulation, inspired by the initial ideas by Richard Feynman more than 40 years ago, to study essentially fundamental physics or chemistry problems or other fundamental science problems by mapping a complex problem, or complex Hamiltonian more precisely, into the system, into the dynamics of a system that we can control and tune with very high precision. And this is exactly the case of our quantum computers. If you're interested in having more details about the technology and the type of use cases we can develop with Aquila, I definitely suggest to look at this archive paper that we published more than 2 years ago by now, with a clear characterization of these three major areas. Now, the second and most recent project that we've been pursuing at the development of the product is our second generation quantum computer, still a system with more than 200 qubits. It has been installed at AIST, which is one of the largest research centers in Japan, the equivalent of NIST in the US, alongside the so-called ABCIQ supercomputer that will host hundreds of GPUs from NVIDIA, together with a quantum node that is provided by QuEra. And the picture that you see on the right is exactly the machine that we've been installing. As you see, there is a core which corresponds to the QPU, and some control racks that you see on the side that are important to essentially make the computer function with all the tools that we inherit from classical and quantum computing. The other point that I want to make is related to the possibility of integrating this device with the current, with existing, and of course also the future generation of classical HPC centers. And interestingly, one of the key features of our technology, given the kind of relatively elementary way to connect to this HPC center, is the relatively low power consumption. Which corresponds to a few kilowatts, up to 10 kilowatts of power, and therefore much less than what actually classical supercomputing system typically requires. And this is important, of course, for our potential future applications, also of hybrid computing, meaning by combining classical and quantum resources, where potentially some very complex type of algorithms could be eventually offloaded into the quantum computer either for better performance or a lower energy consumption. But of course, I want to emphasize that many of these use cases are still essentially under investigation in order to understand which could be the preferred direction of execution of complex workloads. One area where definitely we can start observing a very good advancement of the technology is the area of quantum error correction. Over the past couple of years, QuEra has made really a lot of progress based on the results that we obtained either within QuEra, for example, the experimental demonstration of logical magic state distillation that has been published, that appeared on Nature last week. But we also collaborated a lot with Harvard and MIT and other academic collaborators to make a lot of progress both on the experimental as well as on the theory side. And because of these important achievements, we've been named as one of the breakthrough of the years by the journal Physics World. Now, moving a little bit more on the kind of commercial engagement with other major stakeholders across government, industry, and academia, we work very closely with each one of them to provide access to quantum computing, either through our cloud services or by installing quantum computers on-prem. And this installation comes also with the very dedicated support and the effort from our scientists and engineers to develop the community around quantum computers, around the hardware that we've been developing. The second pillar is focused more on the core development of the technology by doing a very close, very strong collaborative research with some top-level academic groups to advance the areas of quantum error correction or hybrid algorithms that, as I mentioned before, are potentially relevant for applications in the area at the intersection of classical and quantum computing. The third direction that we are pursuing, both with academics, but most importantly, perhaps with industry, is the field of application co-design, where the goal here is really to combine the unique capabilities of current or existing and potentially upcoming hardware generations with the tools that we want to implement at the algorithmic level in order to make them compatible with the current technology and exploit the most of what we have to offer today in terms of hardware. Recalling or emphasizing for those that might not be fully aware of the existing status of the technology, that quantum computing, especially at the hardware level, is still at relatively early stage. So in order to get to the fault-tolerant and scalable regime, we still need to improve a lot the qualities of the hardware, but also to adapt the algorithms in such a way that we can improve or we can extract real value, both for fundamental research as well as for industry applications. So in order to really move the direction of the technology along the path of quantum utility, we decided to create last year the so-called Quera Quantum Alliance that corresponds to a partnership model that focuses on the adoption of neutral atom quantum computing across a wide variety of business verticals and geographical locations. For examples, we have, as you can see from the list of the existing customers or the existing partners, we have both quantum computing companies as well as classical computing providers, HPC centers, system integrators. And I'm happy to announce that recently, actually yesterday, we made the announcement of one of our guests today, Horizon Quantum, as part of the Quera Quantum Alliance. So with this, I would like to conclude the first part of our webinar today, my presentation, and give the floor to our colleague Tommaso De Maria for his presentation on the company Entropica Labs. So Tommaso, the floor is yours.
Thank you. Thank you so much, Tommaso. And it's great to be here while I look for my slides, which you should be able to see in a second. Let me again
Yes.
say thank you to you, Tommaso, to the QuEra team for organizing the event today. I mean, I think it's great to be able to showcase all the really excellent work that is happening in Singapore. And I really would like to start by reminding everyone who's tuning in that despite being a very small country, we've been able to punch much above our weight. And a lot of the great work, especially in software, as you can see from today's guests, that is happening in Singapore is really fantastic. That said, today I would like to say a few words about what we are building at Entropica and where we are positioning our stack in the context of the whole quantum computing industry and technology. So in case you're not familiar with our work, what we do is to build the software infrastructure for fault-tolerant quantum computing systems. And today I would like to start by showing you the team and who we are. So we are headquartered in Singapore, although we have a global outlook and some of our people are working from overseas. We have scientists, engineers, and theorists across actually more than 10 nationalities. And our expertise really lies in quantum error correction, fault-tolerant compilation, and the design of quantum programs. And I would like to continue really that the best segue to introduce what we are doing at Entropica is to emphasize something that we are seeing and something that is becoming more and more real as we grow as an industry in quantum computing. Something very interesting, which reminds me of what has already happened in classical computing decades ago, is that the ecosystem is starting to break down into multiple layers. And the most, well, the fundamental one, if you may, is really the quantum hardware layer, where you have anything that goes from electronics to decoders to multiple ways to build QPUs or physical qubits. There is a connecting layer, if you like, between the hardware and the developers, which I will get to in a second. And that is what we call the quantum error correction infrastructure layer, which is in a way something new. QuEra's has done a lot of incredible work in quantum error correction, and overall the industry is moving QEC at the forefront of innovation today. But I still emphasize that what we're seeing today is fairly recent compared to all the innovation that has gone into building better qubits in the past 10 to 15 years. And what we need is an infrastructure that can connect the hardware, the qubits, the QPUs, with the developers, so that we can actually foster at the top of the stack, if you like, at the top of the ecosystem, very active and growing group of people who can build applications and algorithms that can run in a fault-tolerant way on quantum computers. And if the picture is not clear enough, what we are doing at Entropica is to build the infrastructure that connects the hardware with the developer's layer. Basically, the physical qubits and everything that you need to control the physical qubits, with all the complex architecture on top, which includes programming languages, dev tools, front ends. And today's talk, by the way, or today's seminar is really great because in a way, we have QuEra building the hardware, Entropica building the quantum error correction infrastructure layer, and Horizon building the developers layer. There are overlaps, but I really like how overall the ecosystem is starting to have clear layers, and we're seeing more and more companies occupying and becoming leaders in this layered ecosystem. And our ambition is to unify together by building the quantum error correction software infrastructure. If you have done any work in fault tolerance or error correction, which are sometimes confused as terms, so here I'm trying to be very comprehensive and emphasize that quantum error correction is how you can enable fault-tolerant quantum computations. And when you bring together all these concepts, what you have is what we call fault-tolerant quantum error correction. And if you have ever worked in the field, you will know that FTQC is incredibly complex. There are multiple challenges when it comes to demonstrating error correction. There are even more when you want to be able to run or support fault-tolerant quantum computations. And here I'm just emphasizing 3 of these key challenges, specifically because this is where we at Entropica are spending a lot of time and effort to build the infrastructure to overcome those. If you think of this layer approach or this layer visualization of the stack, what happens in quantum computations is that you move from logical instructions produced at a higher level of abstraction to physical instructions that can actually run on a quantum computer. Somewhere in between that, you need to inject quantum error correction. Once you have done all of that and you have a way to describe your quantum error corrected computation, what you need to be able to do is to pass this information to what we may call a fault-tolerant operating system, which is really a orchestrator, a software orchestrator that tells all the different components of a quantum computer how to run the quantum error correction cycles. This needs to happen in real time and needs to happen in a tight lockstep manner. And last but not least, if one goes to look at today's software stack, first of all, for error correction is very limited, but it also is incredibly fragmented. And if you want to move any program across QPUs, this is really something very difficult to do. We're not even talking yet of systems where you may have multiple modalities or multiple QPUs interconnected among each other. This is what we are addressing at Entropica. As I said, we're building the software infrastructure for fault tolerance. And the 2 main programs that we are creating are called Loom and Quilt. What Loom does is to automatically transform quantum algorithms, the logical layer operations, into error-corrected programs. So then now you can pass these operations or this instruction to Quilt, which is the orchestrator that runs them in real time on ideally any quantum computing platform. This is our ambition, and this is what we are building. Of course, what we have is still clunky, but still needs work. But we have already started to ship out some of our tools. Let me see if I can actually run the video. Yes, great. So I can work while I speak. So right now we are in what we call phase 1 of Entropica rolling out our stack to address these needs and overcome these challenges. And what we are offering to our partners and customers are software tools to accelerate quantum error correction. Specifically, we've built what we call the Quantum Error Correction and Fault-Tolerant Labs. These are software-based solutions that help you to benchmark quantum error correction schemes, to implement quantum error corrected programs, and to analyze trade-offs if you want to run error corrected workflows. We're working with a number of partners, including Horizon Quantum, and I know that Joe will say a little more about that during his presentation. But we're also working with companies that operate at the control level, like quantum machines, software and hardware like Xanadu, and software emulators like QPerfect. And what you're seeing here on the video, and I can run it again, just for a few seconds. This is our graphical user interface that allows you to work with the surface code and explore how to perform lattice surgery operations in a very intuitive and fast way. Then you can take all of that, run it on Steam, or run it directly on IBM quantum computing systems. Okay, so let me wrap up. And before I get to my conclusions, I also want to show you how easy it is to build, in this case, quantum memory experiments in Loom, our translator. So if you want to work with the surface code, all it takes is about 10 lines of code. You can write it in Python. You would define your quantum recorrection code blocks, the operations for a memory experiment. You can compile and run everything on Steam. And what you get are the typical quantum memory experiments results, which, at least in our case, before we had all the software available, would have taken many days of painful coding. Now it takes about 30 seconds of Python programming, which is actually quite great. If you want to learn more, if you want to understand how we can help you, here are our contacts. You can book directly a 15-minute call with us using the QR codes. But really, there are multiple ways to start. You can get access to our cloud quantum recorrection lab, so you can run quantum recorrection experiments on real hardware. We can help you to wire Loom into your stack. We're already connected with QuEraQ, PennyLane, and if you have your own libraries, we can help you to make your existing workflows quantum recorrection ready. And if you're an educator working in academia, teaching quantum information or quantum recorrection classes, we can make it very easy for you to accelerate all of that work by onboarding you with our visual interfaces to simplify how you teach recorrection to your students. Again, thank you so much, Tommaso, for the invitation. I hope I didn't go too much over time with my presentation. If you have any question, please let me know. Otherwise, we can also talk later at the end of all the presentations. Thank you.
Thank you so much, Tommaso, for the great presentation. And let me also remind our participants that we have a Q&A window where they can essentially interact with us in real time. While Joe perhaps starts sharing his slides, maybe Tommaso, I have a quick question for you. So from your perspective and Entropica, what do you see as a kind of immediate opportunity for collaboration at the ecosystem level? I'm really talking about between software and hardware players, especially, of course, with what concerns your company in Singapore and within the all the APAC region more broadly.
For sure, it is a very good question. So today we are working with multiple hardware companies actually, and the value proposition for them is very clear. There are multiple choices to be made when it comes to designing and creating the future generations of quantum hardware architectures. And a lot of these choices, first of all, are very costly and time consuming. And they also depend on how these companies want to or wish to implement quantum error correction in their qubits. So what we can do for them, we can give them all the software tools that they need to understand trade-offs between choices. First of all, they can experiment with multiple error correction schemes. They can see how their architecture adapts or not to these schemes. And overall, this really helps them to inform the best path forward when it comes to designing and building the next generation architectures for their devices. It's a very natural collaboration, actually.
Excellent. Thank you, Tommaso. If we see if there are any additional questions for the participants, I would like to remind that we're not actually taking questions live. We don't allow the participants to speak, but definitely they can raise their questions and ask and interact with us through the Q&A. So with this, I would like to give the floor to Joe. Joe, please, the stage is yours.
Thanks very much. And it's a pleasure to be here, having just announced that we're going to participate in the Quera Quantum Alliance yesterday. So it's a really good timing on that front. We're really looking forward to making use of your hardware. So what we do at Horizon is to tackle what we see as one of the two main problems of getting to useful quantum computing. Now, this is a little bit subtle in that Tommaso has mentioned the importance of fault tolerance, and that's definitely there. But the way I kind of break down this in my head is that one of the problems you have to get to useful quantum computing is that you have to build sufficiently capable hardware. But sufficiently capable hardware is not enough. You also need to build a software layer on top of that. You need to build applications on top of that to take advantage of that hardware to actually get a real advantage out of it. So what we're doing at Horizon, we've set ourselves a fairly ambitious task of trying to bridge the gap between classical computing and quantum computing. So what we've been working on is to build a bridge all the way from code written to run on conventional computers to code to an accelerated implementation on a quantum computer. So what that means for us, what we want to be able to do at the end of the day is take code that was written to run on a conventional system, to run on your laptop, to run on a cluster, whatever it happens to be, to automatically construct a quantum algorithm from that. And that means pulling apart the code, refactoring it, trying to break apart loops, trying to break apart recursive function calls, replacing those with more efficient quantum algorithm building blocks, let's say, to construct an overall quantum algorithm for the particular problem you're trying to solve that behaves exactly the same way as the classical code. And then, okay, we have a high-level description of a quantum algorithm, but now we need to make that run on a quantum computer. And that means we need to compile that down into a lower-level representation that's portable, that can work across many different hardware systems. We need to be able to optimize that program. We need to be able to map it to the particular hardware, to any connectivity graphs, to any movement operations, if qubits can physically move, for example, in ion trap or in neutral atom systems. We need to map to the native instructions for the system, and we need to package it all up for execution. So for us, the end point of development is actually that the program is wrapped up as an API, so it can be directly integrated into any front-end technology. So whether that be a Python script or MATLAB or C, or whether it be even an Excel macro, something like this. So we want to make it as easy as possible to build and manage quantum programs for hard problems. And the reason we want to do this is because we think a lot of the expertise necessary to build quantum accelerated applications are all in physicists, quantum computer scientists, and so on, who are not experts in the domains in which the systems will actually have application. So few of us would be expert in quantitative finance, for example, or in molecular simulations, or in computational fluid dynamics, or any one of the whole range of different application domains where quantum computing is really likely to see use. And our solution to this is to say, well, okay, maybe we can build tools that allow developers that are domain experts in those areas to take advantage of quantum hardware without having to become quantum computing experts themselves. Now, this is really challenging. And when you start out on this path, you say, okay, we're going to automatically construct quantum algorithms. The problem you run into is that quantum computers are supposed to be better computers. They're computers with an extra operation, effectively the Hadamard gate, the ability to get interference between different branches of a computation. The problem is they are not better computers today. They lack many of the features that would allow a classical program to run on a quantum computer even without acceleration. So many lack the ability to do control flow or to do loops. It's certainly basically impossible at the moment to do general classical computation in parallel with your quantum computation. And it's really challenging as well to there is just no support for a lot of the services that would normally be provided by an operating system, like dynamic memory allocation and things like this, that you need if you want to do an efficient implementation of a given program. So what we found is that we've actually had to, with this broader goal in mind, we've had to go back to the drawing board at the lowest level of the stack, build up our own assembly languages that are in some sense a bit more general than those that are currently available at the moment, and then build up tools on top of that. So where we stand today, what we have available in Triple Alpha, which is our IDE, is the ability to write code at this kind of high level of abstraction, to write programs in a kind of basic like quantum programming language, to write subroutines in it from C and C++, and to compile these down to run on quantum hardware. We've been able to demonstrate the building blocks of automated synthesis of quantum algorithms standalone, but they're not integrated into our system yet. And it will take some time before we get there, before we have that complete chain. Because really we're trying to speed run the entire history of computer science. So we're having to, start from let's say if quantum computing is in the equivalent of the 1940s or early 50s at the moment, and we're trying to get up to, kind of present day capabilities, there's a lot of work to do there. So the lower levels of this, as I say, high-level programming language, being able to compile that down, run, deploy as an API on different quantum hardware, that's wrapped up today in Triple Alpha, which is our integrated development environment. And within that, you can write a program in our language, and you can target it at basically almost any hardware. So whether that be superconducting systems, trapped ion systems, soon neutral atoms, or whether it be compiling to models like measurement-based quantum computing, which are necessary if you want to support many kinds of photonic architectures. But what I would say is that our approach to, what it means to program a quantum computer is significantly different to many of the other development tools that are available at the moment. In particular, I like to kind of classify quantum computers into, let's say, 6 types. So let's say type 0 are non-universal systems. So the kinds of annealers that D-Wave make, for example, or boson samplers, which are not full quantum computers. They can't do everything a quantum computer can do. They can't run Shor's algorithm. They're just this more restricted model of computation, but they may still be hard to simulate. They may be able to do things classical computers can't, but they're not a full quantum computer. Type 1, I would say, is the most widely used one you see at the moment, which is circuit evaluation. You give a list of operations, one after the next. The system executes those in order and returns the result to you. If you want to go a little bit further than this, and this has been very popular over the last 4 or 5 years, you can start generating your circuits, the circuits you evaluate on your quantum computer, with a classical computer. So you might have a Python script that generates a quantum circuit, you execute the quantum circuit, you get results back, and then maybe you tweak the quantum circuit and you evaluate it again. And this is very useful in NISQ algorithms and variational algorithms like QAOA and VQE and things like this. But this doesn't capture everything that a idealized quantum computer can do. And you start to see this now when we talk about what's necessary to do error correction, for example, where we need to be able to do fast feed forward. We need to be able to do a mid-circuit measurement in a computation, and then we need to make a decision based on the outcome of those measurement results. Maybe not just a lookup table, but actually being able to do some computation based on that and triggering operations to be applied based on those measurement outcomes. If you go a step further, you can think of this more general setting. And this I'll call kind of type 4 quantum computer, which is to say that you have basically a classical processor that decides what happens on your quantum computer. So it is sending the instructions to your quantum computer to tell it what operations, what gates, or what pulses to send at any particular moment. But it's also receiving signals back from the quantum computer. So, you can think of these as measurement results coming back to you. So this is very natural in the fault tolerant setting where you want to execute some part of a circuit, make a measurement on it. That's going to give you a bunch of syndrome measurements that you then need to feed into a decoder, which is some kind of classical computation. And the outcome of that classical computation is going to tell you the corrections you're going to apply to the quantum computer. And in principle, you may have flow control in this. You may have loops. You may have the equivalent of a while loop where you're repeatedly doing something, for example, with magic state distillation, until you see, hey, yes, I have prepared a good magic state. So you can start to get into these situations where you need support for while loops and things like this that really aren't possible when you're looking at a more circuit-based model. And then the final type, I would say, the pinnacle of what a far future quantum computer could ever hope to be is basically that same thing, but where you add not just the ability to do classical communication into and out of the system, but you also add the ability to do quantum communication to other quantum systems. And I call that type 5, and I don't know of any more capable quantum computer that could possibly be imagined. If you have some ideas, you can let me know, but as far as I can see, this is the absolute pinnacle of what quantum computing can be. So we try to build our languages to target type 4 and type 5 quantum computers, but we try to build our compilers and runtime environment to take that code written for those systems and execute it on type 1 and type 2 quantum computers. So to be able to run it on today's systems. And that means that we're able to add in capabilities like mid-circuit measurements and concurrent classical compute. And we enable this by basically stitching together multiple runs using post-selection. And that gives the effect of being able to do these more complex operations on more limited hardware. So we're able to effectively add new capabilities beyond what the hardware supports. So the ideal model for us then is that we're thinking about a quantum computer, a classical control system that is sending some operation sequence to the quantum system and receiving some signals back from measurements, and that is interacting with the outside world through inputs and outputs. At the lowest level, we structure our assembly language in blocks to enable this flow control. At the top of each block, there's a name for the block. We always start at the start block. But each block, they have this header with a name for the block and a list of the possible blocks you might move to next. And within that block, there's just some set of instructions. And those might be reading inputs, for example, through an API interface. They might be classical computation. So you can see this where there's a multiplication here between frac and pi to give angle. Or they might be quantum operations, for example, allocating free qubits to A, B, and C, or doing various kinds of quantum operations on them. And these might either be at the gate level or at the pulse level, whatever it happens to be for the particular system we're working with. But at the end, we have a transition rule that just says how to move to the next block. So that might either be halt, because your computation is done. It might be advance, because there's only one possible successor block. So that means just move on to the next thing you were going to do anyway. But the most interesting one is branch, because that allows us to say, based on some classical variable that may have been obtained through measurement, what are we going to do next? And we can use these blocks with these simple instructions to construct loops, to construct selections like ifs and cases and switches, things like this. But it allows us to do everything, because ultimately these are the building blocks of effectively a flowchart. And what we can do then is we either try to execute that on hardware that can actually support that the computation of that in real time, and basically very little hardware supports in that direction at the moment. We're building a hardware testbed here at our office in Singapore to be able to implement some of this in real time. But we also execute it via what we call circuitification. So we try to run the program as far as we can up until we don't know something. And that gives us a circuit that we can then run, or some information that we don't have that we can read in through the API interface or from a classical computation. And then we take that new information into account. We expand the circuit further. And we keep repeating this process. And what we do is we keep running. So if, for example, we needed the result of a mid-circuit measurement, we would simulate the control systems up to the point of not knowing that measurement result, but needing to use it. We would then run what we have on hardware. That will give us a sampling of what that measurement result should be. We then take that into account to unroll it further. We run again, and then we just check to see, did we get the same measurement result this time around? If we didn't, we throw it out and we run again. But this allows us to do mid-circuit measurements. It allows us to do full flow control on a really wide range of hardware today. Above this, we have Helium, which is our basic programming language, but this enables you to do some quite advanced things. It's a bit friendlier than having to work with these blocks, so you have more familiar equivalents of for loops and if statements and so on. But it also allows you to do some kind of advanced things, like in this case, including some code that was written in C to run on your quantum data, to run on data that is in quantum superposition. So what we're doing is we're taking some code, we're including a C2Q file that tells us how to generate a quantum circuit from that classical code, just telling it, what's the function we want to compile, what do we want to use in place or out of place operations and so on, some kinds of optimization metrics like this. And then when we pass this through the compiler, we get a quantum implementation of this program. So we can use this to take code that was written in C and turn it into a quantum circuit, which is really quite powerful. So I wanted to give you just a couple of glimpses of what this looks like. In particular, if you use that C to Q chain where you're taking some code that's written in C or C++, and you're compiling it through our system, it turns out it's extremely efficient for constructing certain classical functions that you may want to evaluate on superpositions of quantum data. So, for example, there was a paper from the Goldman Sachs quantum team back in 2021 where they were looking for, what was the threshold for a quantum advantage in derivatives pricing, and so they'd done resource estimation on pricing two different types of derivatives. But what they found was for those programs, the bottleneck function was actually just computing a classical function on a superposition of quantum data. Now, this was inside a quantum Monte Carlo algorithm, but it's just building that kind of classical oracle that gets used a lot in quantum computing. And what we saw is that implementing that function, which was e to the minus x, implementing that in C and just compiling it through our system led to more than a factor of 100 improvement on the overall gate count, the number of Toffoli gates necessary to implement that particular function, going from, for 21-bit precision, going from 15,500 down to 140 Toffoli gates. So it's a really, really significant reduction. And by being able to do this, I think maybe you'll appreciate that if we can really reduce the gate count, if we can really reduce the resource requirements for our quantum algorithms, we can run them on nearer term devices than would otherwise be the case. So it kind of pulls in that horizon of when are we going to see a real quantum advantage. It's not just a hardware problem, it's also a compilation problem, it's also an algorithms problem. The system we have at this point, the ability to do branching instructions, to do concurrent classical computation, also makes it a pretty ideal testbed for being able to implement exemplar error correction and fault tolerance experiments. And we've been very happy to be able to work with Entropica Labs, who've been using our stack for some experiments with their tools. And that's been really good for I think for both of us, hopefully, because it's, in some sense we're very complementary in that they're very focused on the error correction side, and we're very focused on the on building the infrastructure to be able to execute code on a very wide variety of hardware in its most general form, including concurrent classical computation that you need for decoders and different kinds of things like this. And lastly, I would say that, we've been able to use this also to demonstrate things like interactive quantum computing for the first time, where you have a human that's interacting effectively live with a quantum computer. And And this is because of the fact that we're stitching together multiple runs with post-selection behind the scenes, so we can effectively have infinite quantum memory. It's not really infinite quantum memory, it's multiple independent runs. But what this allows us to do is have a kind of Python-like environment where a user can type in instructions to their quantum computer, they can make some measurements on it, and then they can decide what to do next, and it will behave as a single persistent session. The same way as if you're interacting directly with a basic interpreter or a Python interpreter or something like that. So I'll leave it there, but just to say that we're seeing new advances really very regularly now. It's clearly happening all across the industry, but at Horizon, for us, we're starting to see the elements of a kind of nascent quantum operating system emerge. And I don't really mean an orchestration there. What I mean is many of the functions you see in an OS kernel, like dynamic memory management, which we've already implemented in our system. We've added additional models, so we can now support MBQC and other non-circuit models. We've put in a very general optimizing compiler at this point, so that we can optimize arbitrary instruction sets. So we can take code written in some gate set, convert it to another gate set, and be able to optimize no matter what that gate set is. We don't take into account mathematical properties of the gates. We compute them all ahead of time, and then when you run the optimization, it will always find optimizations. So even if you have dephasing gates, it will realize that two dephasing operations, one after the other, can be pulled into a single dephasing operation, and so on. We've added finer grain hardware control with things like pulse level access, and we've started to build our own hardware testbed here, as I mentioned earlier. Putting together our first system here. It's superconducting, but maybe we'll have a neutral atom system at some point in the future, and I would look forward to that. So let me leave it there, and thanks very much.
Joe, thank you so much for the presentation. I think it was really clear. I have a question, and at the same time also a curiosity. You spoke about application, a specific application coming from financial, for financial applications. I wanted to get a better idea of how Horizon is actually approaching with the tools that you've been developing, potentially other business verticals that are potentially very promising for kind of near-term utility for quantum computing, for example, chemistry, material science, and so on. So how do you see the tools that you're developing as kind of crucial to enable this transition towards utility?
Yeah, that's a great question. And what I would say is where we have started from, at least my view was that it was necessary to build up tools to be able to implement more complex programs than are possible in many existing systems. I'm not a huge believer in the utility of variational algorithms. I mean, there's an open question there, and there's still a lot of science to be done to see whether there are really significant advantages to be seen from those algorithms. But from my perspective, I've always been focused on looking at this kind of post-NISQ era. So when we get into the low error regime, whether that's through error correction or through other means, what we can do then. Because this is the regime where we see really large quantum advantages from things like being able to do large quantum Fourier transforms, in Schur's algorithm, but also to accelerate linear algebra and all sorts of different things. And our focus has been on getting to a much broader quantum advantage rather than a narrower one. So that's why our focus has been on, can we build this path to classical computing? Because really the way I see quantum computers is I see them as computers all over again. They're better computers. And so we should be able to apply them broadly. So a lot of the work we do on algorithms isn't specific to a particular industry, but rather it's, can we come up with quantum algorithms to accelerate the evaluation of control flow? Can we use them to accelerate the evaluation of various kinds of operations of different kinds of data structures or data types, so that we can accelerate a really broad range of code. Now that said, we're at a point where we're expanding pretty rapidly, and that will likely mean an applications team focused on a couple of key verticals, but not generally on those areas, but on particular kind of lighthouse problems where we believe there's a really enormous advantage to be had if we can get those implemented. But that will be an internal effort within Horizon. Of course, it opens lots of opportunities to engage with enterprise and to engage with other research institutes. But that's kind of the approach we've taken to applications. We don't think we can do every part of this. We don't think we can do every part of quantum computing well ourselves. We have to take a collaborative approach. I'm not an expert in quantitative finance. I'm not an expert in chemistry. I'm not an expert. Well, we have some machine learning efforts internally, but I wouldn't call myself an expert in that either. But these are areas where it's very clear that there can be an enormous quantum advantage to be had if we can get into the right situation on hardware and on software to take advantage of that. And that's where we're at. So we're really delighted to be partnering with QuEra as really a leading, actually one of the most exciting hardware technologies that I'm at least in my view at the moment. Like, neutral atoms are really exciting. Ever since we saw the error correction demonstrations from Harvard 18 months ago, whatever it was, it's really neutral atoms seem to be moving extremely fast. No pun intended on that. So excited to be working with you guys. Exciting to be working with Entropica as well, and with others up and down the tech stack.
Thank you, Joe. Thank you, Tommaso, for being with us today, being excellent presenters and co-host of this very exciting webinar. And of course, thank you to all the participants that joined us today. I hope that this session offered some useful insights into not only our technology, but our partners' technology and how it could fit basically this growing Singapore quantum ecosystem. We see at QuEra a very strong potential for collaboration across many different stakeholders, government, industry, in particular the growing quantum industry, and of course we are eager to keep building those connections even further. For those that might be interested in reaching in having more information, feel free to reach out to us, QuEra, Entropica, and Horizon. We will be definitely very happy to continue this conversation. So thanks again, and see you next time. Thank you.
Thank you very much. Bye, everyone. Thank you.